What is up, guys? Welcome back to the channel. Thank you for joining us. In this episode, we're doing a deep dive into the oil surge. We're doing a bit of an analysis on what happened, how it happened, and how we're going to stop it from happening in the future. So it's going to be a bit of a technical one. Stay with us. You're going to like it. Alright guys, so we're going to start in the data. So I have on board with me an AIM Solo 2 data logger, and that is connected to the ECU masters, which I use to run the engine. But obviously the AIM Solo 2 data logger is connected to the ECU masters over CAN. So everything that the ECU masters sees, the data logger logs through various channels that have been pre-mapped and all of that good stuff. So, and obviously I have certain sensors. The one sensor and the things that I'm logging are oil pressure, RPM, etc. So what you can see over here on the screen is the lap that I had the oil surge. And I showed a bit of this in the last video, but essentially what we're looking at here are two things. We're looking at the red line, which is basically an RPM trace. They call it a trace. That's the line that shows you your revolutions per minute, your RPM, and then the blue line is the oil pressure. Okay, and I dug into this a bit in the previous episode, but something to take note of is pretty much what I said in the last episode, and that is where we lose oil pressure. And we seem to lose oil pressure on the brakes in particular and going around corners. So here we see massive oil pressure loss on the brakes. Again, we're down to 1.6. Here we're down to 1.3. And if I just move on further down the lap, here you can see that there's through sunset for some reason oil pressure is fine. But then when we get to, and on the brakes here it's fine, but when we get to the first part of the S's at Kyalami, we pick up oil surge again, and basically we lose oil pressure. Again, as we go through the lap, getting onto the brakes up to what we call West Bank, it's the top of the hill, really hard on the brakes here. We go right down to 0.086 bar. And we can even insert the lateral acceleration, and you know, it gets a bit confusing if you start to look at too much. Here we go. We can add multiple different screens. So if here's GPS lateral acceleration. So here you can see getting on the brakes, we pull up to 1.78 Gs, and that's where we see the biggest dip in the oil pressure. And the other thing to note is that was the first thing that stuck out, right? The other thing that stuck out is looking down here through what we call the mine shaft. If we come down the hill, this is where a corner I was worried about. It's very high speed, very high load. We can even put in GPS speed here. Just search for it. GPS speed, we add that as a trace. GPS speed is right at the bottom. When we go through the mine shaft here, okay, there we start losing oil pressure. We're doing, that's almost the peak of our speed, 165 k's an hour. Point I'm getting to is that kind of mid corner here, you can see the speed scrub off a bit. I think I tapped off a bit there. We're seeing the peak oil pressure drop. So we're seeing it on the brakes, we're seeing it through the high speed corner. Here we see it as well. It's a very high load corner. So then I thought, okay, well, there must be a way to calculate how much oil we lose per second, because a common way to resolve this problem is to basically box the sump and put in trapdoors and all of that. So I was thinking, okay, if we can increase the volume, how much time extra would we have? You know, if it loses a point of pressure per second kind of thing. And I started doing the calculations and looking at it, and basically what I got to was it happens so fast that it didn't make sense to just purely add volume in terms of oil. It happens within 0.1 of a second. You go from oil pressure to nothing. And that's kind of what I'm showing you. I try to do some calculations based on box sizes that we can add to the sides, and trying to come up with a concept and a design and calculate how much more oil we need. But it doesn't actually work like that. And then what I did, this is the process of trying to eliminate it from an engineering point of view. Then I went back to the data and I thought, okay, let me have a look at it again. And then something very interesting stood out for me. So what I saw here, I'm not sure if you can see it. It's happening here on the brakes, and it's happening here through the corner. Can you see it as well? What is happening is we're going from 4 bar pressure to 2 bar to 1.8, like that. And we're talking about the time of, it's like a second. And then I look at it again here on the brakes. And what that tells me is something is happening where the oil is there, and then all of a sudden it's not there. And it's not as though it picks up a bubble where it goes away and it catches pressure again. That would be this kind of spike here. You'd see it like a spike like that. A drop and a spike and a drop and a spike. No, we're seeing it from a point of view where you see pressure, then you don't. And I thought, wait a minute, it must be sloshing. So in other words, it must happen so quickly that the oil is there and then it pushes up due to the loads, or it pushes forward due to the braking load. Another thing that indicated it to me is if you look at the oil pressure trace as I turn into the mine shaft, you see that the oil pressure drops away as I turn in, but then it comes back, which means that it is sloshing, it pushes up against the side of the engine and then comes back. So in other words, the energy of the oil pushes the oil away, but then the energy of the rest of the oil brings it back down. That's why you see the spike come back. You see it happen a few times in a couple of different corners. You see it here as well. So the oil sloshes away and then it comes back, and then as the load continues, the oil pressure goes away and then eventually comes back. And then I thought, okay, is it happening everywhere? And I went and looked at the corners where it's, where we lose pressure, and again here you can see it goes from pressure, it's 4 bar down to nothing, 1.4 in an instant. And that tells me, okay, it's not so much the oil's pushing away slowly through high loads and it's draining. No, the oil is sloshing away, meaning that it's so hot that whatever baffling we have, it's not adequate to handle that slosh. Because what happens is when you're running the engine, you might have X amount of oil. Let's say that your oil level is like this. Then you start the engine, the oil level will drop because the pump pumps it throughout the engine. Sure, you've got run back, but there's a lot of oil caught up in the engine all over. So your oil level drops down, that's the one factor. And then you're running with this amount of oil, and if you're not holding it in a position or in a catchment area, sufficient enough to deal with the load, what we're seeing is like more of a slosh load rather than a gradual seeping away of the oil, then it's going to pick up air, and the pump will pick up air. And then I thought, okay, well, let's try Google some simulations on this and see if we can find anything. And that's when I came across this. I did some research and some digging. I found this is a fuel tank sloshing simulation with and without baffles. So simulation software, it's basically a software package that can simulate using millions of little particles the flow of a fluid, or they call it CFD software, analysis software. So that's you can do it with gas, with air, with fluids. It's very expensive software, and I searched some of it because this has to have been searched before. And speaking to some of the engineers I work with, they mentioned look at some of the work that's been done on fuel tankers, trucks that carry fuel, because if a truck is driving along and it hits the brake, all of a sudden the fuel is going to rush to the top, and then you get the energy from the fuel pushing the truck forward. And if you're talking about, I don't know how many thousand liters of diesel, you're talking about how many tons of force and energies that's going to push that truck forward. So there's been work done on this, and that's when I found this. I thought, okay, let's have a look. So you play the software and you can see the slosh effect here. So this is applying a lateral load. You can see exactly what it does. Now I'm not so much worried about the baffles. I'm more looking at what happens when the horizontal load is applied to it. So you see in the corner here how it pushes up. That for me is super interesting, and I think that is exactly what is happening. Now even if we have the baffles, you can see that you still get to a point where it draws air, and we sitting with a scenario something a bit more like this, the left hand tank. So I think we're dealing with something similar to this left hand tank, and the challenge we have is a bit deeper than that, because the challenge we have is that the shape of the sump is quite narrow. In other words, the bowl that actually holds the oil is quite short and narrow. It's also at an angle, whichever angle it is at. So we're dealing with this problem, but also the oil is in a very, very small area and the sump is angled. So when you apply this kind of load to it, it just simply sloshes out of the way. Now why would it do that when we have a baffle already in place? We've baffled it, we have the windage tray, we've got this ring at the bottom, we've done a lot to try and limit the surge. Yeah, you've got a side view of it. Here we can see a sump, and you're applying different loads to it, and it's more accelerating loads. They're getting on the brakes, trying to see what happens in the corners. There you can see it's sloshing back. Not sure what's the brakes and the acceleration here, but you can kind of see the slosh of the oil, and that's our biggest problem at the moment. If you want to see some more of this kind of content, please consider subscribing. Just click on the subscribe button, hit the bell, and you're good to go. That kind of helped me identify the sloshing effect, and that is exactly what I think is happening. So we know through the data that we go from oil pressure to no oil pressure. We've looked at the simulation. I need to understand why it's doing it. So I took a look at the design of the sump, the design of the baffling system we have. So you can see from the back the position of and the angle of the sump, and you can see the windage tray is there. So if we take the windage tray out, you can see exactly how we've baffled the sump, right? So we've got a top plate that kind of mounts to different pickups we've put in there. You can see that you can see the angle the sump is sitting at, and the box, the pan I was talking about. So we've got actually quite a small volume within that pan section that we have to work with. Here you can see the inside of the sump and how we basically put a ring around the pickup, but our challenge really is on this side, and that is the right hand side of the car, and I'll show you exactly why now. So we have this little gap in between that baffle plate and the sump. The windage tray fills that gap. As the windage tray goes in, you can see how it fills in that gap. Does not do much, because we're still seeing oil surge in the sump, under brakes and in corners. So I thought what I need to do is get an idea of how much volume the sump actually takes. So in other words, fill it up and see where does the level go to. This sump is supposed to take 5 liters. So I put 5 liters in my fuel can, and that was just F-gas, filled it up, and I was only able to get 3 liters in until the top of the fuel reached the edge of the sump. And I managed to get a little bit more in, but it essentially came down to just over 3 liters. I put 5 liters of fuel in that drum. The sump, according to spec, only takes 5 liters of oil, and what I've managed to get in here is about 3 and just a bit liters. So what you can see is that the oil level actually sits higher than the sump line, because the sump is resting in its natural position. The oil actually sits within the block, right? So that means that there's quite a bit of oil above the line, and the problem with that is as the oil sloshes, it carries energy, and that comes down to particle flow, etc., etc. But if it's sitting above the line, it carries the energy to pull it as it flows up under surge and the cornering loads. It then kind of draws additional oil with it, and if there's a pathway for it to go, obviously it's just going to follow that natural path. So here you can see, I mean, this gaping gap, so that's why it, I guess, through that's the front of the car, so that's the gearbox side. So through left corners would surge right, which makes sense according to the data we've seen. So especially turn 8 at Swartkops here, the last corner, it surges heavily through there, and it makes complete sense. So on the on this windage tray, this is basically to stop the oil foaming, and it makes sense why you would have that. It has this little plate, but I don't think, well, that plate is doing nothing to control oil surge. You've still got a gap here that all the oil can come out, and there's a gap here where all the oil comes out. So effectively that's doing nothing. Also, the big problem we have is getting on the brakes. So I think also with that plate, it's doing nothing to stop the oil rushing forward over here. Again, you've got a massive amount of oil sitting here, and obviously when the engine is running, the oil level drops. So some of the oil is running through the engine, so naturally this oil level would drop. How much, I don't know, but ultimately what happens is you're going to get oil seepage through there, and this oil that's caked up here is just going to slosh up against the front, and oil is just going to come out here. So that is basically what's causing, as well as the oil sitting super high up in the block. I mean, I think the oil line is probably, well, I mean, here we can see that it's already higher here. So if it is sitting, I mean, we've still got another 1.5 liters to go there. So the oil level is sitting up here, more or less. I mean, that's probably 50 mils above, or maybe 30 mils above here. So it could be even in line with this line, let's say. So it's probably just below your dipstick line here, which if you draw a straight line, that's about 30 mils above the deck here. So that's where the oil level is naturally. That means this sump doesn't have enough volume in terms of the design for a race situation. How do we fix that? Well, we've got to fix two things. We need to fix volume, and we need to fix the surge. So to fix volume, we are going to box this out on the sides like you do with a lot of different sumps. So we'll basically add a box here that'll come out straight. It'll be just above the oil line, and probably won't be that big here, but this side it's going to need to come out quite far, and the challenge is going to be the fasteners. How do we get those fasteners in? You know, that's going to be a real challenge to still get the bolts in while being able to box this, because this side is your real problem side. And then in terms of the surge, that's going to be another challenge, but I have an idea for that. Alright, so what I did to find a solution is I turned to a company that has made wet sumps successfully in the past, and I knew about these guys because I had worked on cars with their sumps before. Now this company, I can't really remember their name. It's either Freeline or Burton or one of the British companies that make sumps specifically for the Ford Duratec, the Ford Z-Tech engines, Cosworth, BDA, those engines, the Duratec. And they make wet sumps, and I know that they work because I've personally seen them work on various cars, specifically Lotus 7s, where a Lotus 7 is it's a very low weight car, but it carries a lot of corner speed, very high G's, and if they're going to work there, then yeah, it'll work. That concept will work. So I knew it was a successful concept, and so what I did is I went and looked at their design of sump, and that's what you can see on the screen here. You can see the one on the left, this sump is the one that I am familiar with, and if you open the sump up, you can see, well, you can see with the sump open, the sump has 3 partitions effectively, and oil is obviously stored within these partitions, It looks like at the bottom corner here there is an opening in between the partitions, and oil kind of is allowed to fill in those areas. If you look at the top here, there is a plate that kind of covers this area, and that plate is basically to box the different partitions so that when you get oil surge and slosh, the oil doesn't run away from the system. It's contained within let's say a tank, 3 isolated tanks, but they are linked in using this valley at the bottom here, it would seem. So you're not going to get the immediate slosh away and that immediate drain away from the pickup. You're going to get the oil moving to a different area in the contained area, but it's not going to transition between the different compartments that easily. And then your pickup is kind of in the middle, it would seem, and so that's where it scavenges oil. The oil drains back from the block through these 3 holes, it looks like, and then this plate at the top looks like it's just an extra layer of protection, I guess, should you need it. On the right you've got a similar type design. I'm not sure what this sump is for, but it's a similar concept. You can see the bottom is boxed off. You've got 3 return drain holes, and that also allows the oil to kind of move around in that boxed section at the bottom. Yes, some oil will come out through that little hole, but effectively it's not going to be all of it, and you're not dealing with trapdoors, and so the oil is definitely contained within those areas. And it looks like you have enough volume so that when the engine is running, the oil level drops and it revs up, then you're still going to have enough oil within that compartment so that the oil can so you can have a consistent oil feed to the engine. So you always have oil flow and you always have oil pressure, because ultimately that's what the engine needs to operate. If you look at this picture of the sump, you will see, okay, it's sitting a bit skew, but you will see that there, as I mentioned before, there isn't a lot of volume area within this sump, especially because a lot of the oil actually sits at this level, right? So, but in a race situation, you can't have the oil level up here because you can't box it up here. So we need to add volume at the bottom to be able to still keep the 5 liters, but drop the oil level down so that we can box the top here. Does that make sense? Let me create a crude sketch for you. So what I'm talking about is adding a box here and boxing it out here. It's pretty much what I said before. We're going to add that boxed area to add volume to the sump, right? Then what I need to do is create a plate that is basically going to block off this whole section and close it up. After we've boxed it, we're going to block off this whole section with a similar type design as we saw here. So a plate that's going to kind of block it off and box it up. Going to box the side of the sump as you see here, similar to what we've done there. But on top of that, and you see that here from this side, so we're going to add the wings as I've mentioned before, but on top of that we're going to add, and that will look like this, but on top of that we're going to add this plate in the top here, and that will effectively look something like this, so that we get a foolproof system. We get the volume we need, we close it up, we contain the oil, we'll still have the pickup in the middle, we'll probably still keep this ring that we have there to kind of stop or to limit us from having to put in too many baffles. We might put in a baffle over here just to stop the oil surging up here and moving out of the way. It's going to want to come up here on the brake, so we might do a small thing here, but it still has to drain down. So that's the plan really. So it's twofold. and I think we're going to be able to have a foolproof system if we stick to that concept. What do you guys think? Let me know in the comments. Do you have any ideas for a design on a wet sump? A wet sump is quite a complex thing. You're trying to contain oil, and at the same time you have to put oil back in, but you have to keep it from moving around, and if it moves one way you still have to get it to move the other way, but still keep it contained. So it's quite a complex thing we have to do, but I have some good guys that I'm going to be working with, and I'm pretty sure we could pull this off. Unfortunately it didn't work the first time, but that's how it goes with race cars. So you have to just go through the design iterations, and often it's time and money, but that's just how it is. It's development. But anyway, if you like this, you know what to do. Thank you so much. Again, if you have any inputs, please put it in the comments and let me know what you think. What's your designs? Do you have links? Put the links down. Let's have a look and maybe come up with something cool. Obviously a dry sump system is the best way to go, but the cost and the complexity of that is significant. So if we can get away with a wet sump, it's a great win. Anyway, thank you so much for watching. We'll catch you guys next time. Ciao, bye.